on the possibility that LIGO may have detected dark matter, although I must say that, like in any Bayesian statistics, the key issue is what's the prior on that. But if you give it some finite prior, then it's not ruled out. And today we'll start with Ilya Mandel, who will talk about tidal disruptions of binary stars. He was a member of the LIGO collaboration until July, and as coincidentally, at the same time as Brexit took place, he decided to leave the collaboration. But it's not correlated.
Not at all. Although my wife blames me for causing Brexit.
And he's currently at the University of Birmingham. Afterwards, we'll hear from Simon Bird that gave the ITC colloquium. He's at Johns Hopkins University, and he will talk about detecting damped Lyman alpha systems with machine learning. And actually, that is your main field of research, hydrogen at high redshifts. Yeah. And then we'll hear from Mateusz Ruszkowski, who is visiting us from the University of Michigan. He gave a talk in the High Energy Division earlier this week, and he will discuss simulations of Fermi bubbles. And finally, we'll hear from our own student, graduate student, who is graduating this year, Mocz. And he will talk about moving mesh simulations of star-forming cores in Magneto-Gravo-Turbulence. Ilya.
Thank you, Avi. Thanks for the introduction. I think this is my second time giving one of these lunch talks, and the last time I did talk about LIGO, and nobody seemed very interested. It was about 5 years ago. But clearly now all of you are very excited. So I'll talk about something else. Maybe hopefully this will mean that 5 years from now, this will be a very exciting topic too. We'll see. So I wanted to talk about tidal disruptions, but not just tidal disruptions of single stars, tidal disruptions of binaries. And this is work done with my student Ben Bradnick at Birmingham and Yuri Levin in Australia at Monash. So I don't think I need to review the basics of tidal disruption for the audience, but just keep in mind that this is a picture that we've had since Martin Rees's work and those of his collaborators now almost 30 years ago. A star comes close enough to a massive black hole that it is tidally disrupted by the gravitational forces of the massive black hole. About half the debris is unbound, half the debris is bound, but in extremely eccentric orbits. Eventually it comes back, probably has some kind of interaction, self-interaction within the debris stream that causes shocks. Those shocks emit radiation. Hopefully that's what we're seeing when we look at the tidal disruption events. And then, of course, the mass return timescale has this characteristic t to the minus 5/3 behavior. And this is a telltale signature of the light curves of tidal disruption events. And there are now a number of observations of tidal disruption events, as well as careful simulations of exactly what the hydrodynamical simulations of what a tidal disruption looks like. And the predicted light curves seem to match a number of tidal disruption event candidates. Okay, so far so good. So what if we have a binary instead of a single star? Well, here's a binary. It consists of my collaborator Yuri and myself. Yuri is a very good tango dancer. I'm not, but let's suppose for a moment that we're pretending to dance tango together. And because I'm not a very good dancer, bad dancers on a dance floor tend to bump into other things, and so I kind of lead us a bit too close to this massive black hole that's sitting over there. And so we come close to this massive black hole, and well, we all know what happens. What happens is that, of course, our nice binary is tidally separated. So one of us ends up plunging into the black hole, getting tidally shredded in the process. That's our tidal disruption event. Another one is ejected off to infinity as a hypervelocity star, and Scott Brown, I can't see Scott, but if he's around, then Scott goes out and detects Yuri flying off as a hypervelocity star. Okay, so that's a standard picture, and everybody's comfortable with that, except it turns out that's not necessarily what happens. And the way to think about what actually happens is to imagine this little picture of a loss cone. So here is the loss cone for tidal separation of the binary. Here's a much narrower loss cone for the tidal disruption of an individual star, right? A star is much smaller than a binary, so you need to get much closer to the massive black hole to be tidally disrupted than for the binary to be tidally separated. And typically, if I have some star that is, or some binary rather, that actually is sitting out at some very large apoapsis, is going around on a very eccentric, let's say, roughly parabolic orbit around the massive black hole, then a little perturbation at apoapsis, because there's this huge lever arm, can send this massive binary all the way into this single star tidal disruption loss cone. And if that happens, what we expect is that, in fact, what should happen is that, of course, the binary gets tidally separated first, but then both stars are almost on the same trajectory around the massive black hole, so in fact they should be sequentially tidally disrupted. Now, of course, on the other hand, if we are sitting relatively nearby, we have only tiny steps in angular momentum space around the massive black hole as our binary gets perturbed at apoapsis, and so the loss cone is empty here. We never end up plunging into here. We first sort of cross this boundary. The binary is tidally separated. One star indeed flies off as a hypervelocity star. One star plunges in. That's actually not quite true either, but I'll get back to that in a second. But let's actually consider these systems. And remember, roughly half the systems in a dynamical situation are in the full loss cone regime, half are in the empty loss cone regime. So this is not all that rare. And so what happens now is that, in fact, we both end up, yes, we've been tidally separated. We're no longer on a bound orbit around each other, but both of us on a nearly identical trajectory end up falling into this massive black hole. And now we have, in a non-negligible number of cases, since I'm running low on time, let's skip this, we have something that looks like this, right? This is very much a mock-up. We did not do a proper hydrodynamical simulation. We only looked at the dynamics of binaries, but we found that something like 5 or 10% of all tidal disruption events should actually be these double-peaked tidal disruption events, where first one companion and then the other companion of the binary are tidally disrupted. So our prediction is that if you look closely, you should actually see that there are a fair number of these double-peaked tidal disruption events. Now, is that actually borne out by the data? Well, it's not very clear. I'm going to skip these visualizations for a moment, but here is a data from that recently, just this year, is coming from Ogel 16 AAA. Well, there seems to be a second peak there. We have to wait a bit longer to see whether, in the end, we see the telltale t to the minus 5/3 decay that we think would make it a confident tidal disruption event detection, but or candidate at least. But maybe there's a chance. What about this guy, Assassin 15LH? Well, actually, one of these teams claimed it was just a supernova. Another one, though, claimed it was a tidal disruption event. So there's, of course, as usual, a big question about where it is. There is some evidence that maybe a tidal disruption event simply from where the kind of host galaxy it's coming from. It's quite a massive host galaxy with a very low star formation rate, which is not where you expect to see from other observations superluminous supernova. So maybe it's a tidal disruption event. And there seems to be some evidence, again, for possibly a rebrightening or a second peak. So maybe this is another double tidal disruption event. Okay. One other interesting thing about tidal disruption events, we think there's some evidence that at least in some cases, we see gamma ray bursts in jets associating with tidal disruption events, right? So this is the famous Swift event from 2011, which of course made a lot of news. I think there were 4 different Nature and Science papers on this one event alone. One trouble with this is, and the explanation is that you see this gamma ray burst, this very unusual gamma ray burst, because you're actually on the axis of a jet that was formed during the tidal disruption of a star. One problem is to form a jet promptly, you need a pretty strong magnetic field, and it's kind of hard to figure out where this big magnetic flux is coming from, given that previously this seemed to be a very quiet source. There doesn't seem to be any evidence of an AGN sitting there before this tidal disruption event. So what was anchoring this magnetic field if there was not much of a disk there? Well, one interesting possibility is, let's go back to this picture of our empty and full loss cone. Let's consider for a moment the empty loss cone and ask, well, is it really empty? What actually happens in the empty loss cone is not necessarily that you have this tidal separation, hypervelocity star plunge into the black hole. What actually happens in many cases is that you have a tidally induced merger. In fact, a tidally induced merger is the more likely outcome than a tidally induced binary separation. And so now you have a merger product, and this merger product actually on a time scale of 10 to the 5, 10 to the 6, okay, maybe 10 to the 7 years, is very likely in turn to eventually get tidally disrupted by the massive black hole. But now you've got this merger product, which, first of all, during the merger itself, you've wound up the magnetic field, so you can enhance significantly the magnetic field strength. Then possibly there are multiple near flybys, which could also enhance the magnetic field strength. All of it taken together means you actually have a much stronger magnetic field potential than you would have during a single star. So now if you disrupt this merger product, maybe that could actually explain where this high magnetic field would come from to generate the kind of magnetic flux that you need to form a jet promptly. Okay, so I think probably I'm at the end of time. So just by way of summary, two predictions. One is around 5 or 10% of all tidal disruption events will actually turn out to be double tidal disruption events, double peaked events. But one of the big questions is, what is the actual self-interaction looking like? And what would the spectrum really be? How easy it would be to distinguish these? So this requires actually proper hydro simulations, which we have not done. And probably tens of percent of binaries in the empty loss cone regime would actually merge before the merger product is tidally disrupted. And so this could have a special observational signature, such as, for example, this magnetic field enhancement, which would allow prompt jet formation. Thank you.
Intersection of the streams and the formation of the disk that feeds the black hole. So that delay could be a year. So the question is, if you have two stars and you have a very long delay until the streams intersect, can you actually tell if there are two peaks?
So I think one of the questions is, what is it that you're actually seeing? Are you seeing the accretion at all? And my guess is that what you're seeing is always the shocks and never the accretion. I think the accretion happens indeed much later. It takes a long time to circularize the ejected streams. I mean, the ejected streams are hugely eccentric. I mean, forget about whether you have one tidal disruption event or two tidal disruption events. You have this extremely eccentric thing. That's not going to accrete onto a black hole. You need to circularize it first. That can take a very long time. And by the time that happens, actually, most of the emission has already happened. And if the very fact you are seeing this t to the minus 5/3 slope, that's the return time scale. That's not the accretion time scale. It actually suggests that what we're seeing is really the return time scale. So we're seeing the shocks. That's the luminosity that people are actually observing. And so in that case, I think the answer is that yes, because the two stars are following a very similar orbit, just because the relative angular momentum the difference in the angular momentum, the relative angular momentum within the binary is tiny in comparison with the angular momentum in the center of mass of the binary around the massive black hole. So the orbit is very similar. They will typically self-intersect on a time scale. If it's let's say, a million solar mass black hole, it's going to be on a scale of a month or so. So I think it's actually quite plausible. But it's also possible that indeed it could be a much longer delay, for example, if it's a more massive system. And so there is a sort of Merloni et al. Paper on something that used to be classified as a tidal disruption event, and then people said, oh, wait a second, 5 years later or so, there was another spike, and people said, well, okay, it can't be a tidal disruption event anymore. Well, maybe it could be if it's one of these things. So I absolutely agree. The timescales could change a lot depending on the details.
Questions? You explained things so clearly, there are no questions.
Or I bored everybody again. But I promise you, in 5 years, it'll be exciting. Thanks. I'm going to leave this to you.
Hello, can you hear me? Hello? Okay. Right, so thank you all very much for coming to listen to me. I'm going to talk about something which is somewhat different to what I talked about in the equilibrium. And those of you who know me will know this is a little bit of a departure to me because this is something to do with data. So normally I'm a theorist, but this is real observational stuff. This is work that working on with Roman Garnett, who is a statistician at UWashington, and Shirley Ho, who is Lawrence Berkeley and Carnegie Mellon. So we're going to look at teaching computers to detect DLAs. So what are DLAs? DLAs are neutral hydrogen absorption features in quasar spectra. So this is a quasar spectrum, and this marked with this big arrow is the DLA. So the problem here is that you looking at this quasar spectrum, it's pretty easy for you to figure out where the DLA is. This is a relatively nice example, so it's not always quite so easy. But for a computer, it's a little bit difficult. So the traditional way these things are detected is with visual inspection. So some poor grad student sits there and looks at this quasar spectrum and says, yep, DLA, click. SDSS-3 has 200,000 quasar spectra in it. Future surveys will have an order of magnitude more. It is clearly unreasonable to expect a grad student to sit there looking at all these quasar spectrum. So we can't do visual inspection anymore. Instead, we want to teach a computer to do this. The basic problem is... my computer is going bananas. The basic problem here is that... I'm going to sit here and hold the keys. The basic problem is that the quasar spectrum is noisy. Not only is it noisy, it contains other absorption apart from the DLA. It contains Lyman alpha absorption most prominently, and also various metal lines. So what we're trying to do is we're trying to teach a computer that this thing is qualitatively different from this thing. Computer doesn't want to show you both of those. And this is not something that's obvious to it because it's kind of stupid. So how are we going to do that? We're going to use Bayesian inference. If you want to detect something from data and the data is kind of complicated and you want to have rigorous errors, you use Bayesian inference. We're going to take a training set of known DLAs, so a bunch of quasars which are known to contain or not to contain a DLA. And in this case, we use SDSS DR9. So that's nice because the noise properties of DR9 are similar to DR12. We will feed all these quasar spectra to a machine learning algorithm, which using Gaussian processes to describe both the quasar and the non-DLA absorption. And this will give us a prior, firstly a prior on the shape of the quasar without a DLA, and secondly a prior that the quasar has a DLA, and priors on the properties of that DLA. And this is all explained in this paper, which I don't have enough details to go into, or Avi's clock will beep at me. So what this gives us is a posterior probability for a DLA in any given quasar spectrum, and a posterior probability for its condensity and its redshift. And this means that we can build an accurate model for the population of these things, even with relatively poor detections. So even though SDSS spectra are extremely noisy, some of them have signal-to-noise ratios less than 1, and they don't necessarily distinguish noise from signal, even in this case, we can build a model for the DLA population. And this is more interesting than just for you people who might be interested in neutral hydrogen, because the DLAs are also a contaminant for cosmology. And if you're trying to get a Lyman alpha power spectrum, if you're interested in, say, BAO or redshift 3, you need to understand the DLAs so you can remove the foreground for that. What do we get? This is what we get. So this is the column density distribution function from our method. The black points with error bars are from an earlier data set from DR9, and the blue points are our method from DR12. So the blue error bars are the 68% confidence intervals, and there is a blue error bar on every single point in that plot, but you can't see them because they're very small. and the gray band is the 2 sigma error bars. And I should mention that the column density distribution function is basically a PDF with some unusual units. So this is basically a histogram of the column densities of neutral hydrogen in the universe. And 2 points of this is, firstly, we reproduce quite well the earlier data sets, which is great. You know, this helps you have confidence that our method is working. And secondly, the error bars are extremely tiny. And this is because we are able to use the full data set. So the previous data set was restricting it to particularly good spectra, and this is using all the SDSS spectra. This is the omega DLA, so this is the amount of neutral hydrogen there is in the universe as a function of redshift. Again, we agree pretty well with earlier measurements. It's roughly constant up to redshift of about 3, and then it starts to increase. We're actually getting a measurement up to redshift of 4.2, which is kind of amazing because there are no very good spectra at that redshift. We don't have a lot of secure DLA detections. But because we have probabilistic detections, we can still say something, even though it's not a lot. The error bars at redshift 5 are enormous. Even though it's not a lot, we can still say something about the population. And again, we're in pretty good agreement with previous work. You can also detect the line density of DLA. So this is the probability that you'll see a DLA in any given spectrum. The fun thing about this plot is you see that the black plots, the black points, which are previous work from DR9, they do not have error bars on. The reason they do not have error bars on is that the author of that paper felt that it was way too hard to quantify the uncertainty in his measurement. Because what he had was a bunch of spectrum that he looked at and said, this is a DLA and this is not a DLA. And he thought it was just too difficult to quantify the selection function that he induced by this. But because we're using some rigorous Bayesian method, we can put error bars on our probability that something is DLA. And so we can quantify the uncertainty in this. So that's great. And my final slide is to say that we have this method for automating detection of these objects in the spectrum. It's a Gaussian process machine learning thing. I mean, machine learning is a strange word because the machine is not really learning. But we have a nice way of fitting for these things and distinguishing a fit with a DLA for a fit with without DLA and with just the quasar continuum. We get a posterior probability for each of these things for this large catalog, and we can use that to measure the population of neutral hydrogen in the universe quite well. So I think I'm successfully under time, so thank you. You're talking about this thing between redshift 3.5 and redshift 4.5. Yeah, so that is interesting. The other interesting thing is that, of course, it is in earlier data sets as well. So one thing that you might find a little bit suspicious is that redshift 3.7, the Lyman limit line redshifts into the visible. So any quasar spectrum with a Lyman limit trough will suddenly become visible around them. So that might be screwing up SDSS's color selection in some way, is my best guess for why this happens. This certainly occurred in earlier data sets, but I thought it was fixed. People told me it was fixed for DR12, but maybe there's a little bit left. The other thing that could be happening is maybe there's just some redshift error in these particular quasars. I mean, if you take a few of these quasars at redshift 3.5 and their redshift's a little bit higher, then this goes away. Of course, it could also be a real effect, and I don't know what that would be because that's this is a data paper, so I'm trying not to theorize too much.
Did you give your algorithm just the spectrum, or do you also feed it things that have already been estimated, like redshifts, for instance?
We feed the spectrum and the redshift of the quasar. So there's some indication that the dominant source of error in the algorithm is error in the quasar redshift that is estimated. Because, well, if the quasar redshift is a little bit misestimated, then some of these lines, some of these emission peaks will be like slightly offset, and the algorithm could potentially determine that as a bit of absorption. We feed it. we feed it some physics. So it knows about Lyman alpha and it knows about Lyman beta. And it knows, of course, about the void profile shape of the DLA. So there is a certain amount of physics that goes into the algorithm. But the data input is just the redshift of the quasar and the spectrum. And the noise, sorry, and the SDSS noise pipeline estimates.
Do you find this experience more rewarding than teaching a student?
I think certainly I find it more rewarding than the student would find clicking 2 million times rewarding.
There are no more questions. Let's thank Simeon again. And while Mateusz picks up, I want to mention that we had the opening of the Black Hole Initiative this week,
All right. I'll tell you about simulations of Fermi bubbles that I've been doing with Karen Young, who's actually leading this project. She's an Einstein Fellow, so I'm sure you will hear from her pretty soon. I think Einstein Fellowship Symposium is probably coming up. This is work also done with Ellen Zweibel, leading expert on plasma physics and linear momentum conservation. And so I want to put it in context a little bit. So yesterday during the head colloquium, I told you a little bit about cosmic ray feedback in general, and we went through a range of scales from small things such as M82, where I was trying to argue that these winds could be launched by cosmic rays. So these are cosmic ray assisted galactic winds. Then I also discussed a little bit about feedback on much larger scales, where cosmic rays also quite likely play a role, and we really try to quantify how important they are. And so you can put this in perspective and ask a question, why is it that we really care about these things? Well, we care about feedback in general, and cosmic rays in particular, because it can help us to explain, for example, the distribution of relative number of halos as a function of mass. At small scales, we will have feedback from galaxies in form of winds, and I would argue that cosmic rays play an important role over there. And on the other hand, at very large scales, you will have feedback from supermassive black holes, and again, here cosmic rays could be important. So what I want to do now is to focus on kind of intermediate range and talk about something that many of us really care quite a bit about. In particular, Doug cares about this object, Fermi bubble, right? Is there there should be there? Well, I'll just keep on waving my hands. So Fermi bubbles. This is an example of with a nice picture of a Fermi bubble inflated, quite likely by a central black hole, and these structures here are filled with cosmic rays. You can also see the structures in microwave emission. This is Planck haze. And so what we are trying to do is we are trying to test a hypothesis that these bubbles, that emission from these bubbles could be explained in the framework of so-called leptonic hypothesis, where emission is accounted for by the same population of electrons, both in the microwave band and also in the gamma ray band. So basically what we are trying to do is we are trying to incorporate these two very well-known processes, such as synchrotron emission, where electrons or positrons gyrate around a magnetic field line producing gamma rays, or process whereby a low-energy photon, such as a CMB photon, gets kicked by fast-moving lepton and produces a gamma ray. So this is radio, this is gamma. So this is the basic picture that we have in mind. galaxy, outflow from the galaxy, and yellow circles correspond to this haze emission, and purple ones correspond to gamma ray emission. And so in this picture, this gamma ray emission comes about because cosmic rays upscatter cosmic ray micro radiation that fills the space and produces a gamma ray emission here, versus this emission here that comes from magnetic field inside those bubbles that interact with the same population of cosmic rays. So that's the basic framework that we've been pushing. Many other people also looked at this in detail, and we published a number of papers, and I'm going to tell you about one of the results that is coming up in this paper that we are finishing. So what other constraints can we put on this model? And so here is one interesting relatively recent constraint, and this is a constraint on the spectrum. So we can take the spectrum, gamma ray spectrum from these bubbles, and plot it as a function of the distance away from the plane of the galaxy. And the answer is that the spectrum is pretty independent of latitude, of the distance away from the disk. And it's also characterized by this sharp cutoff. So the question is, can this leptonic hypothesis account for this cutoff? That's the basic question that we are trying to address. And in order to do this, we have to do a lot of coding. And so I will not bother you with the details of coding. I will just say that Karen led this effort by building on our previous work, and she implemented spectral evolution of cosmic ray population. So now, instead of just following bulk energy density of cosmic rays, we can actually look at how cosmic rays evolve in different energy bands. So we can, in other words, produce a spectrum of cosmic rays and then translate the spectrum to the radiation spectrum. And there are various physical mechanisms that are implemented in this code, and it's probably not worth spending too much time on this right now, given time limitations. But I just want to focus on the result from this exercise and tell you if it's consistent with what you have just seen on this slide. Can we really account for this sharp cutoff in the leptonic scenario? So first thing you can do is just plot total energy density in cosmic rays in these bubbles. This is just a cross-section through one of those bubbles. And you can see that variations are actually quite large. This is a scaling for the energy density, and variations here are actually quite large. This is total energy density. So it's essentially a product of typical energy of a cosmic ray particle and number density of particles. So we can argue actually, or we are arguing in this work, that these variations are predominantly due to the variations in the number density of cosmic rays and not variations in the energy. So if you look at maximum energy of cosmic rays in these structures, it's much less variable than total energy. So this is the picture here. Variations here, the scale is a little bit different. Variations are very different. So if you just forget about the skin of that bubble, here you have predominantly values comparable to around 100, and this is in GeV. So most cosmic rays here will have maximum energies of around 100 GeV. So basically, we expect the distribution of this cutoff in the spectrum to be pretty much independent of position across the image of the bubble. So that's the bottom line. But then the question is why it's happening, and I will just this is my one of maybe penultimate slide in this presentation. Why is this happening? So top panel here shows you maximum energy of a test particle in this bubble. It changes quite a lot in the very beginning, but then later on kind of saturates. So in order to answer the question of why there is no spatial variation, we can basically look at different characteristics, timescales in this problem. Dynamical timescale on which cosmic rays are advected away from the center. Adiabatic timescale on which cooling occurs due to adiabatic expansion. Inverse Compton losses that produce the gamma ray emission that we see, the upscattering of CMB photons to gamma ray band, and synchrotron emission due to gyration of electrons in the magnetic field. And so the shortest of all these timescales, apart from the very beginning here, is the timescale associated with just advection. And advection doesn't really do anything. If you just take a blob of cosmic rays and move it from one place to another, the spectrum will be the same. Okay? But the spectrum is basically determined very early on. Here in the very beginning, when you look at the very central regions when the bubble is being formed, here the shortest time scale is inverse Compton time scale. So something interesting happens in the center. All particles are in kind of the same environment. There's causal contact. The spectrum is determined, and then the whole thing just slowly moves away from the center. So basically, spectrum is determined very close, and then particles are just dispersed in the bubble. So that pretty much explains why there is cutoff that does not depend on position across the sky, because just simple advection does not really alter the spectrum anymore. It's kind of reminiscent of, it made me think of inflation. You have early on in the expansion, things are in causal contact, and then you expand this whole universe to larger scale. So in some sense, there's a certain analogy between these two. So this is a bottom line from this exercise. Leptonic model can naturally account for gamma ray emission, synchrotron emission, and it can also naturally explain a cutoff in the spectrum that is independent of latitude. So that's one of the tests. And maybe in a more broader context, I would like to argue that cosmic rays are generally very important for the modeling of physics of feedback in various contexts. In the context of, let's say, modeling galactic winds, in the context of modeling much bigger structures at the opposite range of mass spectrum galaxy clusters, and also for things such as the Fermi bubble. So your really takeaway message is that cosmic rays are important. Your executive summary is here. So I'm sorry for being 14 seconds late.
These bubbles were inflated 15 million years ago.
Yeah. That's one of the interpretations. There is also an alternative interpretation that is due to winds. But in this model, bubbles were inflated by an Aegean jet a few million years ago.
And so these things happen all the time.
Yeah, they could, yeah.
Question over there. Was it?
Ask an easy one.
Okay, that your dynamical time is defined how exactly?
Dynamical time is defined as a constant length divided by this speed. That's the definition that was used for the purpose of plotting time
I
scales.
mean, if the scale is 25,000 light years and it's 100,000 years, then that's a quarter the speed of light is the advection speed you're assuming.
Let's see. We are talking about. I'm just trying to.
I was just surprised
Yeah,
by
it's
that
not-
because we actually had kind of thought it's a problem that the spectrum is the same going all the way up. But you're saying it's not a problem.
It's not a problem at all. It naturally comes out of this model. In fact, the spectrum that we inject extends way beyond the cutoff of about 200 GeV, and the physics works out such that it's just right where it's supposed to be. Yeah, I'm happy to answer this question that you asked in more detail. My laptop has just froze, but we can talk about it. Yeah.
So, when I think of advection, usually also associated with either compression or expansion.
Yeah, we separate the two.
Okay, but you have no adiabatic cooling?
We do.
expansion?
We completely do. And the plot that I was just trying to show, Doug, that I cannot because the laptop isn't working, separated timescale due to cooling due to adiabatic expansion from the timescale associated with just simple advection. And it turns out that the advection timescale that does not have adiabatic expansion factor in it is the shortest of all.
Sure, but you still find that your maximum energy is constant everywhere.
Yes.
If there was any expansion, I would have expected that guy to decrease.
Yes, and that happened early on in the simulation. And once this happens, there's not so much expansion. It's mostly just taking this blob and moving it.
At constant density.
Just displacing, moving the cosmic ray population from one place to another. And that is not dominated by squeezing or compression.
The standard law is that supernovae dominate the cosmic ray production below 10 to the 15 electron volts or so in the galaxy.
Yeah. I wish I could
Do you
get.
expect the sanitary case to contribute to that significantly, or is it negligible?
In terms of galactic population, most of the cosmic ray population would come from the stars. So what I was going to go I was going to go to the opening slide. Most of the emission, gamma ray emission in the disk would come from supernovae. And so I don't think Fermi bubbles are contributing to that budget very much.
Not much at this position of the sun.
Right.
I don't see much.
I would say, I would agree with your statement.
But keep the hadronic cosmic rays separate from the electrons, right? They're very different. timescales.
This has woken up. Okay.
Okay, hello everyone. I'm Philip Mocz, and today I'll talk about moving mesh simulations of star-forming cores in Magneto-Gravo-Turbulence, and this is work in collaboration with my advisor Lars Hörnquist and Blake Sleeberghardt and Chad Hall here at the CFA. Okay, so a big overview picture of the types of simulations I'll be showing today are these turbulent MHD boxes where I turn on self-gravity, and which leads naturally to the formation of protostellar cores, and you're used to understand the role of magnetic fields in the collapse and create also mock observations on polarization images for karma and future ALMA observations. Okay, but first I want to talk about the numerical method, which is a large part of my PhD, developing MHD for a moving mesh code, which is really necessary to obtain the dynamic range to simulate the collapse of these systems over a large number of large order of magnitude. Okay, so it's really a best of both worlds approach where I combine the shock capturing capabilities of static mesh codes with the Lagrangian adaptive nature of smooth particle hydrodynamics codes on a moving mesh. And this has a nice property of being able to capture advection exactly at the numerical level. Okay, but a big complication with solving MHD numerically is this unassuming equation, the divergence precondition, div p equals 0, which is just one of Maxwell's equations. The point is it's not needed to evolve the system. It's just a constraint that is if it's satisfied at all times, it should be, it's satisfied at all times if it's satisfied at p equals 0, just as that there's no monopoles in your solution. And this is necessary to maintain for accuracy and numerical stability. And the standard approach to solve this on a fixed grid is the constraint transport equation, constraint transport method, which exploits Gauss's theorem from calculus to solve the magnetic field on face centers instead of volume centers, and calculates the electromotive force on the edges of the cells. And this is tricky to implement in a moving mesh code because your faces deform and can actually disappear or reappear. Okay, but it's done in my paper 2014 where I keep track of the face average magnetic flux representation, and I use a method to reconstruct the flux on faces that appear and disappear. Okay, but to zeroth order, you're keeping track of the magnetic flux shown in the top equation here, and you're calculating the electromotive force using the electric field in the face frame. And in ideal MHD, this electric field, if the face is moving exactly with the fluid, this is 0. So this is just a statement of conservation of magnetic flux. And in my 2016 paper, I reformulate this method using a cell-centered vector potential formulation, which simplifies the method greatly and improves the efficiency. Okay, so just some simulations with this method. We have the point is machine precision control on the divergence of the magnetic field. This is a comparison with the moving mesh scheme to a divergence cleaning scheme shown in red. And This is a Orsak tank test, which is a simulation of decaying supersonic turbulence. Okay, we're able to also have exact advection with the moving mesh scheme, shown on the left. This is a magnetic field loop test. A static mesh shows advection errors, while a cleaning scheme also, even if you use a moving mesh, you're not able to advect the solution exactly. So finally, also some turbulence tests comparing the constrained transport scheme on a moving mesh with a cleaning scheme. On the right is constrained transport, and constrained transport is very important to maintain other invariants of the ideal MHD equation, such as the mean field, which is highlighted here. We're able to preserve it well, but if you use a cleaning scheme, you actually grow your mean field and you change the nature of turbulence completely, which is characterized by these PDFs and power spectra. Okay, so this is why it's important to maintain divergence-free condition in your simulations. Okay, on to science now. The simulation of star-forming cores. For some background, we know that star formation is a competition between turbulence, self-gravity, and magnetic fields. And very basic theory predicts that as the cores collapse, you might form these hourglass shapes, which has been seen in some observations. There's a big question of how important are the magnetic fields? Are they sub or super alphanic, and on what scales? And what is the origin of the magnetic field structure? Are they inherited from the strong field at large scales, or are they amplified weak fields through turbulence? This is called the magnetic topology problem in the literature. How does the magnetic field topology evolve as the ISM forms, molecular clouds, and the cores contract to form stars? Okay, a great way to study this observationally is to look at the scaling between magnetic field strength and the density. And this characterizes how the contraction happens. So if you have spherical isotropic collapse right here, you get this unique signature of 2/3 exponent. But if you have some filamentary geometry and collapse along only certain directions, you can get a scaling ranging between 0 and 1. 1/2 is a very popular scaling in theoretical models because in an isothermal gas, it means that your plasma beta is constant, so you have equipartition between your magnetic pressure and your gas pressure. Okay, so is this star formation self-similar? So some observations suggest it is. So the 2015 Nature paper looks at the scaling between magnetic field and density for a high mass star forming region on many different scales, down to 0.1 parsec using SMA. And they find a slope of 0.4, so it's close to 0.5. It's really a signature of anisotropic contraction. And they also see, furthermore, these hourglass-shaped morphologies on many different scales. Okay, however, this is in contradiction with Zeeman alpha. So Zeeman measurements of B fields in diffuse molecular clouds by Crutcher, and Zeeman observations are the most robust way to measure the magnetic field strengths. And here the data suggest scaling that's closer to 2/3. So if you have this weak field, isotropic collapse preferred. Okay, and what about smaller scales? Still, this is observations by Chathall here that he talked about at the previous lunch talk. And what we see in certain cases like this Serpens type 0 protostar with new ALMA data, so we see very chaotic field morphology on these small scales that are uncorrelated with the magnetic field direction in the large scales. So what can simulations teach us? So here I've run a number of simulations with my MHD code of a turbulent, magnetized, self-gravitating ISM cloud, very large scale. So about 5 parsec, this is isothermal. And these simulations are characterized by actually just 3 numbers, the sonic Mach number of the turbulence, which we know that ISM is supersonic, so I choose a value of 10. The alpha virial parameter of the cloud, which observation tell us is about 1. And finally, the alphanic Mach number, which characterizes the mean field, large-scale magnetic field, which is really unconstrained by observations. So I test the range of values. And these are the simulations of the star formation in various turbulent environments as a function of decreasing magnetic field strength. When you have very strong magnetic fields, you can form these filamentary collapse with the magnetic field orientation preserved down to the very smallest scales, and you get this hourglass shape that's perpendicular to the filament. And when you decrease the magnetic field strength, you can actually recover. So you don't see filamentary structures on a strong filamentary structure on the small scales, but you do see chaotic turbulent field morphologies. We can study how the magnetic field scales with density. We see that in the strong field case, the scaling goes as 1/2, and in fact, plasma beta is 1 along the collapse. And in the weak field case, the scaling goes as 2/3. And on the outer scales of collapse, plasma beta is actually close to 1/2, so turbulence has amplified the magnetic fields to roughly equipartition value. And the scaling is 2/3, which means that in the cores, you can actually get stronger magnetic fields than you do in the strong field collapse case. Okay, and this is looking at radially average profiles. They actually follow r to the -2 profiles pretty nicely, which is predicted by isothermal collapse models, which don't even include turbulence or magnetic fields. So, interestingly, self-similarity is broken in the weak field case because the magnetic field in the green grows faster than the other quantities. And this is because of the 2/3 scaling from the flux freezing condition as opposed to 1/2 scaling. Okay, so this is just a summary of the conclusions. Contrasting these two channels of star formation, so we can have 2/3 versus 1/2 scaling, isotropic versus anisotropic, turbulent morphologies versus hourglass morphologies, and we also have breaking of self-similarity in the plasma beta parameter. Okay, and then going back to the serpent source, here we can quantify some statistics about the field morphology using a histogram of relative orientations between magnetic field direction and density gradients, and we find that ALMA observations are actually, this is consistent with a super alphanic turbulent environment, so we've caught red-handed in collapse this type 0 protostar, and it has revealed that the star formation of this system occurs in super alphanic turbulent environments, but in general, alphanic Mach number of around 1 might be a good fiducial value for star formation, but star formation may occur in both the greater than 1 or the less than 1 environments, and these have very different consequences for star formation. Okay, thank you. So I'll take questions now. Yes. Yes. Okay. So I think the ambipolar diffusion timescale does become important in the strong magnetic field case, but it operates on slightly on longer timescales than the free fall timescale. So I've only simulated the initial stage of collapse, but if I were to continue the simulations, I would have to include the effects of ambipolar diffusion, especially in the strong field case. So that's also an alternative theory of how star formation might occur. You might have extremely strong magnetic fields, and they might not even collapse from gravity, but you can have ambipolar diffusion forming the stars.
Are you able to trace the flow of gas along your filaments? And if so, is that causing the pores to grow?
Yes. Okay. So I've done some preliminary investigations of that to see whether growth is primarily channeled through the filaments or not. But yeah, I don't have the exact answer to that question yet. Something I'm looking into. Okay, but my guess is that so when the filaments might have large m dot, but it also has a small solid angle. So when you compare that to the accretion from the regions that are not that's not the filament, so there the solid angle is much larger. So the m dot there might be comparable. Yes.
From that, and then also comment on how should it be reasonable then?
Okay, yes. So this is important. So it's important that we're looking at like very early systems here. So isothermal assumption is actually valid up until these scales. And if I were to continue my simulations, the collapse would continue forming adiabatically. So I'd have to change my assumptions. But on these very early type 0 systems, we can assume on these scales isothermal and also neglect radiation. But in general, so those both radiation becomes important and the isothermal condition breaks down. So if you're looking at older systems and you want to know what happens to these turbulent field morphologies, then you need to include those effects.
I just wanted to congratulate you for giving a talk where you start with pure theory and meshed it together with observational data. That's not very common.
Okay. Thanks, Avi. Okay.
There must be like 20 gazillion problems in the source code.
Yeah. Yeah, that's right. So actually, we're looking at like the ratio of E to B mode polarization now, because there's a recent paper by Mark and Chris Hirata that suggests this ratio of E to B mode polarization of 2 is not characteristic of like standard MHD turbulence, and yeah, they think it's a problem. So. So we can look at
Polarization from the galaxy, presumably, right?
So well, okay, they're looking at Planck data where the polarization signature might be dominated by the ISM. So at those latitudes, but it's quite a recent paper actually. Yeah.
Whether or not which one is really the result of a recent merger, that's a possibility.
So let me check when we're meeting. Because you're going to colloquium, right? Yeah. Okay, yeah, I think we're meeting at 3:30 or something. So right before.
I will then see you at 3:30. Like if I should go, I have to go say hi to Anjali the fighter. I should go find John.
Oh yes. Yeah.
And I should also
could this be due to some very
go pick up some things Anjali.
Okay.
much too short to think of how you would get something. The time scales of the stars were days.
Yeah, I think. I mean, I think that there, I think it's not necessarily the